Saxon Advanced Mathematics, Lesson 5. I was just diving into a conversation about complex numbers. So let me pick up where I left off. I already told you about all of this. Here's the format. We're always looking to put our answers in when we're dealing with complex numbers. So let's do example 5.6. And in this, we have a string of numbers that have imaginary components, right? So this fits that style. These are all imaginaries. Checking to make sure I'm copying properly. Okay, beautiful. So we look at this and go, okay, well, what are we supposed to do with that? Oh yeah, we remember that every pair of i's equals -1. Every pair of i's, right? I imagine this. Right? They're frightened. So we can go through here, and remember when we first learned this, we would write out the number of i's, and then you can circle every pair and let that equal to -1, right? You don't have to go through that long process anymore. You can kind of do it mentally, but I'll remind you, okay, so 2 of these come out to make a -1. We'll have 1 I left, so this will be -3i. Here we have 2 pairs coming out, so that's -1 times -1, so that makes it positive. We have 1 I left, so it becomes positive 2i. This stays the same, there's nothing to simplify. Here now we finally have a real number component that will come out of this because we've got 2 i's, they go to a -1, that changes that to -2. All right, these are all like terms, so we can clump them all together. Let's see, we have -3 plus 2, that'd be -1, -4i is what that all simplifies to, if you're with me. But we want to make sure we write it in the proper form. So this is the real number, and this is the imaginary component. So we want to be sure we write it like that. If on a test or a review problem, a student wrote -4i -2 and showed me that as the answer, notice that the components are exactly right, but I would take a point or 2 off for that because that's not a plus bi. It has to be a plus bi format. Got it? Cool. I know you'll never make that mistake. Okay, one more. One more of these problems. Don't even think that we're done. This is a really long lesson. 5.7, ready? Now we've got, it's still a complex number problem, but it looks quite different. What we have here is a long string of numbers that we're adding, and we see that some of the radicals are going to be really super easy to simplify, right? We've got some perfect squares in here. Some of them are going to be less so. Some of them have negative signs, which we know as soon as we see a negative inside an even numbered root, and remember this is a square root, so it's an invisible 2, we have a problem. So that's the first thing we deal with, is we convert every square root of -1 to an I. Now, in our brains, this is what we're doing. We're taking this and we're writing it as square root of 3 times square root of -1, right? We're breaking out the minus sign, and then we're converting that to square root of 3i. That's the process we're doing in our brains, right? Because we know that square root of -1 equals I. Now, we don't have to show that for every step because that's a lot of steps. So I'm just going to show you what my brain wants to write down. That would be 3i. Notice the I is on the outside of the pig house. It's not inside of it. Times, this one's perfectly innocent. We can just change that into a 2 right away. Plus 3 times, this would be square root of 2i. This one would be 3i, if you're with me, right? The square root of 9 turns into a 3. This turns into a 3, but that turns into an I, plus 4i plus 4. Okay, now let's simplify again. Here's a term, little and little. So now we're simplifying within the terms. Let's see, this would be 2 times the square root of 3i, would be the proper way to write that. Plus, okay, we can multiply together the whole numbers, and then there's the radical, and then we have I squared. We'll simplify that on the next pass. I want to finish this. Okay, those stay the same. Now this becomes a minus 1, correct? So we'll have 2 times the square root of 3i minus 9 square root of 2 plus 4i plus 4. Okay, those terms are all simplified as far as they can go. Our last step is to put this in A plus BI format. All right, so we want to separate the real numbers from the non-real or slash imaginaries. This is the real part, but we can't combine them because this has got a pig and a two pig, and this one doesn't. So all we can do is write them together. 4 minus 9 square root of 2. That feels like the right order for me. There's our A. Plus, now let's do our imaginaries. 4 plus 2 square root of 3i. That is our final answer. And all we've done to get from here to here is we just put the real numbers in this set of parentheses and called it A, and then we put all the imaginaries in this set of parentheses and called it B, and then smack the I at the end. That's how we get our A plus BI format. When we have pieces that we can't combine, we use parentheses to clearly indicate who's related to who. Got it? I've been getting a series of really weird emails this week from some woman on Ancestry.com, which I don't really go on. I have had my DNA tested, and I looked around a little bit, but it's just not really my jam. Actually, I found some mistakes in my own family tree, so I was like, this isn't even right. I'm not into it. But I've been getting these messages from a woman who thinks she's related to me, but she's not. And I keep being like, she's like, oh, well, your grandfather and my brother, you know, blah, 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 blah. And I'm like, but that's not, you know, the person you think is my grandfather is, I've never heard of this man before. The person you think is my mother, I've never heard of these names before. Like, where did you get this? And she said, today she told me that I messaged her and said I was married to somebody named Florence DeAngelis. I'm like, I've never heard that name in my life. So I think I got hacked on Ancestry, you guys. And somebody's spreading rumors about my family tree. I don't know. It's weird. But anyway, I just keep thinking about that today. DeAngelis, I have no clue. There was a boy who died of an asthma attack in Mukilteo. Oh, it was probably 15, 20 years ago by now. But he was like a 12-year-old boy, and he had an asthma attack one day like while he was at school, and they called the 911 and all of that, but he died of an asthma attack. It was so terrible. And his name was, I think, D'Angelo. Similar. Okay. Two more topic. Areas of this is a type of problem that test people love to throw at students. It's not hard, but it requires a little bit of strategic thinking. So I'm going to give you the strategic thinking now, so if you ever see this, you won't be fooled. Okay, example 5.8. The scale factor between two rectangles is 4. What is the ratio of the areas? Okay, so let's just write this down. Scale factor equals 4. And we're supposed to find the ratio of the areas. What does that even mean, right? That's just words on a page to me. Okay, what that means is that we have two rectangles. And I don't know exactly what they look like, I'm just drawing. What that means, they each have a width and a length, but the scale factor is 4. What that means is the width of the second rectangle is 4 times bigger, and the length of the big one is 4 times bigger. That's how we use that scale factor information. It's another way of saying it is that the proportion of each to the other is 1 to 4. Okay? So this is, we're going to call this triangle, or not triangle, rectangle A and rectangle B. Okay, so let's find the area of A. Whoops. Well, that would just be length times width, right? We don't have any numbers on that. What about the area of B? Oh, well, that would be 4 times the width times 4 times the length. Remember, order doesn't matter. I'm writing them in opposite orders, but it doesn't matter. This would be right? We can put a 1 in front of that. This would be 4 times 4, so that gives us 16 times L times W. So that means the ratio of the areas is 1 to 16, right? This second one, the area is 16 times bigger than the area of this one. Does that make sense? So the trick is to use the scale factor information to set up the lengths and widths and then calculate the area. It's okay that you're using letters because the numbers are what we're interested in. It's 1 to 16, and John points out that you can also say it as 16 to 1. Okay? I like this because we did little to big. The way our pictures, the way we laid out our pictures, this one makes more sense, but either is acceptable. But the idea here is that you take the information about how much bigger each side is than the other, and then you calculate the areas to answer the question. Okay, that's kind of tricky. It might not sink straight into your brain right away, but that's how we do it. Here's another one that is similar. Example 5.9. The radius of one circle is R. Okay, that sounds familiar. They're using an uppercase R, so I will too. I like to be like John. And the radius of the second circle is 3r over 5. I mean, I don't know if it's bigger or smaller. It's actually smaller, but I'm just going to make the circles look more or less the same. Okay? 3r over 5. What is the ratio of the area of the first circle to the area of the second circle? Okay, so they're asking, if we call this one A and this one B, they're telling us to find the area of circle A and write it as a ratio with the area of circle B. Huh, all right, well, let's just find those two. The area of A is equal to, okay, we know it's pi r squared, and in this case, that would be pi, because we're using an uppercase R, I'll switch it and write it like that, right? And we can put a 1 in front of it, because we're going to be comparing numbers, hopefully. For area of circle B, again, it's pi r squared, and in this case, that would be pi times 9 over 25 r squared, right? Because that's 3 over 5. I squared it, and I squared the r. All right, so let's write that under here. It would be 9 over 25 pi r squared. Now, I've got the two areas, and I want to write them as a ratio, so I can just do that like that, right? That line means ratio. And now I see that the pi and the r squareds cancel, so I can write the ratio is 1 over 9 over 25. And that is a wicked nasty complex fraction, but we can easily fix it. 25 over 9, 25 over 9. This cancels, and so this gives me 25 over 9 is the ratio of area A over area B simplified. That was weird. That was weird, right? But you see how this is the answer, and that's right. Okay, we're not going to do a lot more with those problems. Test takers love this because they think that what they're doing is taking simpler ideas like area and formulas and radius and ratio, and they're asking you a new question about it. And they think they're being very clever and requiring you to think on your feet. And it's really just kind of annoying. But that's okay. We can master that. You'll get the homework to practice that in. All right, last section. We get to draw pictures. Diagonals of rectangular solids. Let's just go right into an example. There's not much to explain, except I'm going to tell you we're going to use Pythagorean. And there are 2 of these examples, and then finally, we're done. All right, John gives us a picture. It is a kind of like a shoeboxy kind of affair. Looks like this. Okay, pretend it's perfect. It's not terrible, but it's not perfect. Now, we can see inside this box. Okay, so you can see through it. It's a clear shoebox. All right, and it's got letters at all the corners. I'll copy those on. A, B, C, and D form this front panel. E, F, G, and H form the back panel, if you will, right? Okay, so we've got a front and a back. That's what we're mostly thinking about right now. Find the length of the diagonal that connects corners B and H. in the rectangle shown. B and H means go from here to there. We're going from the front lower left to the back upper right. Do you see how it's a diagonal? It cuts across. All right, that requires us to break this down in several interesting ways. The first thing we're gonna do is find, imagine that the sun, there's a light source above this and it's shining down. That would create a diagonal like this, right? There would be a shadow down here. We're interested in finding this line. Okay, so what I'm gonna do is I'm gonna redraw the bottom of our rectangle, right? And it goes B, F, C, G, right? It's this. And we want to find this, right? That's the same space on, right? Can you see how those two relate? Now, the other thing that's weird here is we don't have any numbers. Oh, we know that this is X and this is Y. John also told us that. And this is Z. I'm gonna circle those, okay? So we can copy the X is on here and the Y is on here. There are no numbers. We're doing this all in the abstract. Oh my gosh, what the heck, right? But what I can see is that if I want this measurement, this BG, it's gonna be equal to, I can call that C, and then I can say that this is equal to the square root of A squared plus B squared, right? And I can see that X and Y are the legs, right? This is the hypotenuse. Does that make sense? X and Y are the legs. This number that we want to know is the hypotenuse, so I can solve for this. All right, so then we can say BG is, I'm not going to put that segment line over there anymore, that just looks cluttery. Since X and Y are the legs, we can just substitute those in here. BG equals the square root of X squared plus Y squared. That is a value that is useful to us. All right. Now, so that's the first thing. We found BG. I'm going to write that down. Now we've got this going across the floor, but what we're going to do now is use that as a leg, and this is a leg, and we're going to draw another triangle to find that triangle. So let's look at what that triangle will look like. This dimension is equal to Z, right? We have it written on this side, but it would be the same right here. So this is Z. And this line along the bottom is this BG, which we just found out. So this, oh, I don't really have space to write it. I'll write it over here. This is the square root of X squared plus Y squared. That is this. Here, I'll write it this way. This dimension. So we now have another Pythagorean theorem thing, right? We want to find this. This is our red line. This is the area as I marked it here. And then the bottom of this is the orange line, which is what we found here. BG is the orange line, right? So, I wish I would have done this. So we're using our first step information and this height to calculate this line. And again, these two are the legs. So to find this, we're going to take, this is BH. BH equals the square root of z squared plus the square root of x squared plus y squared squared. What? It's just Pythagorean. This is A equals Z, B equals this scary looking thing. And we know that a shortcut for the Pythagorean, I should have written this before. Right? That's a shortcut way to find the hypotenuse, is to take the two legs, square them, and then add them together and take the square root, right? That's just a reorganized version of Pythagorean. So we did this first with x and y, simplified it, and now that number has become one of the legs, and this is the other leg. So now we're squaring both of those and taking the square root, which is just like that. So now I'm just going to bring this over. I'm going to bring this calculation to the next page. Okay. This can't be simplified, but this neutralizes that radical sign. So BH equals the square root of, and I'm just going to change the order. This will become just a plain x squared. This will become just a plain y squared. And then we have the z squared. Okay, so this neutralizes that. There's my first part, there's my second part, there's my third part. They're all added together and we're taking the square root of. This is my final answer. Holy smokes, right? It looks super hard and it is a little mind-bendy, I'll grant you that. But if we can slowly break down where we're taking the triangles and getting the information, life is good. All right, and we have one more that's kind of like this. This is example 511. Grace is having puppy dreams. It's similar. Find the length of diagonal AC in the rectangular solid shown. All right, let's draw the picture first. Going up into that problem, but it's okay. This is also a clear box. Right? Pretend it's perfect. It's not. It's got letters on it. And this one actually is kind enough to give us a few numbers. This is point A. This is B down here. Grace is having puppy dreams. Can you hear her? She's barking in her sleep. This is a 2, the length of that side. This is a 3, but this is an M. Good Lord. Okay, find the length of diagonal AC. That's from up here to down there. It's the same idea as the last one, and we're going to approach it exactly the same. First, we're going to find the length of the shadow, if you will, and then So first we'll be looking at this line as it lays flat on the base of this, right? We'll look at this flat part. And then we'll change the angle and we'll find that part. Complicated, but it makes more sense as we go, I hope. All right, so first I'm going to look at the base. I'll draw it flat. This is corner B, this is corner C, and we know that this distance is 3 and this distance is 2, right? This is my orange line across the bottom, B to C. Here's where we have the orange lines, right? This is just to help you, we don't need these lines to calculate, but it's just to help you see how I'm orienting myself within this box. So we're trying to find the length of segment BC, and that would be, this number is also over here, right? It's the same number. I'm just gonna copy it over there. So we know that when we use our Pythagorean inside out, we can say C equals the square root of A squared plus B squared, right? So once again, we can say B equals the square root of 3 squared plus 2 squared. Oh, it's so much more relaxing when we have actual numbers, right? This is 9, this is 4, so we can say that BC equals the square root of 13. Oh, happy days, right? Now, we're looking at this triangle. It's got orange on the bottom, right? It's this thing that I'm looking at. It's got orange on the bottom. It's got red up here. And I used a red pen to draw lines, so I'll do that again, right? This is this. What's the height of it? M, which is over here, but this measure would be the same as that measure. So that's M, this is A, and this is B, and this is C. What's this? Oh, this is our orange line. So this we know is square root of 13. So now we do the very same thing using this, our inside out Pythagorean, and we're going to do the very same thing. Line AC, or segment AC, is going to be equal to the square root of the 2 legs squared. So M squared plus 13 squared, and that is all we can do. There's nothing more. Oh, yes, we can, because this is square root of 13 squared, right? So these two, again, cancel each other, and we get M squared plus 13 is the length of AC. Let me check and make sure I got it right. 13 plus M squared. Yes, I wrote it in the opposite order, but it's addition, so order doesn't matter. Yay! Okay, that's the 2-step process. Of solving these. First, we draw the shadow on the ground and find the length of that. Then we draw the triangle like that. It's tricky to see it all. If you have problems and can't tell what I'm talking about, let me know in the video chat and we can go over how those triangles are coming together. But if you can see that, then that's the secret of the problem. All right, hallelujah, we're done with lesson 5. Do the odd numbered problems, skip the constructs and the concept reviews, and I will see you tomorrow for lesson 6. Thank you, goodbye.